welcome to the Penguin Prof channel. In today's episode, I want to do some genetics problems. So let's get right to it. I want to make sure everybody's comfortable with these terms. Alleles are different forms of a gene, and we inherit one allele from each parent. What that means is that the alleles you inherit may say the same thing. If they're both dominant, we say you are homozygous dominant for that particular trait. They may also say the same thing, but both be recessive. We use capital letters for dominant, lowercase letters for recessive. The other option is that you might inherit one allele from one parent that's dominant and one allele that's recessive. So your alleles say different things, and we call that condition heterozygous. Hetero just means other. Okay, a lot of genetics has to do with probability, and probability is just a measurement of expectation that an event will occur. Probability values always range from 0 to 1. So 0 means absolutely impossible. 1 means absolutely certain. So of course I convert this to a penguinized scale. So all probability is going to range in value between 0 and 1. Probability turns out to be a little messy when we talk about alleles, and this professor of genetics in Cambridge came up with a way to sort all this out. So I want to show you how to use this square and solve some basic genetics problems with it. The first example I want to look at is the disease albinism. Albinism is the lack of melanin, the pigment in our hair and skin. This lack of pigment is actually due to an inactive or absent form of tyrosinase. This is the enzyme responsible for the production of melanin and actually has copper at the center. Albinism is an autosomal recessive condition, which means that you must inherit one copy of the recessive allele from each parent in order to actually be an albino. So here's a typical problem. What is the probability of having an albino child if the parents are both heterozygous for the condition? So the first thing that you want to do is write out all of your alleles. So in this case, both the parents are heterozygous. So they carry the trait for albinism, but they themselves are not albinos. The question is, if they both carry the allele, what is the probability that they're going to have an offspring that inherits the recessive allele from each of them, that's homozygous recessive, and will therefore be an albino? How are we going to figure this out? Well, that's what the Punnett square is for. So here we have our Punnett square, and the first thing you want to do is sort out the parents. Now in this case, the parents are both heterozygous, so they're both the same. It doesn't matter who you put where. This individual is going to inherit the dominant allele from both parents. They're going to be homozygous dominant. Then you're going to get 50% of the offspring will be heterozygous, and then here's your box with the homozygous recessive. So what this means is that the probability of two heterozygous parents producing an albino child, homozygous recessive, is 1 in 4. All right, here's another one. Huntington's disease is autosomal dominant. What that means is that only one dominant allele is needed to actually inherit this disorder. Huntington's disease is a degenerative disease of the nervous system. So what's the probability of having a child with the disease if one parent is homozygous recessive and the other is heterozygous? So the first thing you want to do, of course, is write out your alleles. So in this case, this is the parent that actually is affected, that has or will develop Huntington's disease. We're going to cross that with a parent that does not carry the trait, homozygous recessive, and we're going to see what happens. So we're going to make our square here. Here's the affected parent, and here is the unaffected parent. We're going to fill out the boxes, and what you're going to see is that 50% of their offspring would actually inherit the Huntington's allele, and 50% would not. So the probability of having an offspring with the Huntington's allele is 2 in 4, or 1/2. Okay, so hopefully so far so good. We're going to start to talk about unions and intersections here, and Venn diagrams turn out to be really helpful to do that. It's a great way to visualize sets, and we're going to use circles to show elements of the set. And of course we're talking about relationships, so I thought, hey, let's talk about relationships. So we're going to have set A and set B in order to illustrate the difference between unions and intersections, and we're going to get to those and or rules for genetics. So set A, if you're looking for a relationship, let's say you're looking for a partner that's smart. Set B, other characteristic you're looking for, someone that's funny. So let's look at the two options. we can have an intersection of A and B. So an intersection is where the two sets overlap. The union is either A or B. So what I mean by that is on the left we have the intersection of individuals with the characteristics smart and funny, where they overlap in the red, versus on the right we have the union smart or funny. So what that means is that an intersection is this and that. It is less likely to occur. So you would say the probability would be lower than the union this or that. That is more likely to occur. And by the way, in terms of relationships, the more characteristics that you add and the more sets that you need to overlap, let's say you're looking for smart, funny, and can dance, then you notice that the intersected regions, that intersection becomes smaller and smaller. Okay, so probability-wise, when you see that word and you're talking about an intersection, that means multiply. So we're going to do a couple of examples, like flipping coins. What's the probability of flipping 2 coins and getting heads on both? Okay, so the probability of getting heads is 1/2. The probability of getting heads is 1/2. So for each coin, the probability is the same. But this and means multiply, because I'm saying I want this outcome and this outcome. So 1/2 times 1/2 gives you the probability of 1/4. All right, here's another one. What's the probability of giving birth to 3 daughters in a row? Now, the gender of any child is an independent event, even though you'll hear people say things like, oh, girls run in that family and so forth. But actually, every child is an independent event in terms of the probability of what gender the child is going to be. So the probability of giving birth to a girl is 1/2. And the probability of giving birth to a girl is 1/2. And the probability of giving birth to a girl is 1/2. The thing is, I'm saying a girl and a girl and a girl. So that becomes less and less likely. And means multiply. So I multiply the probabilities of each. So the probability of giving birth to 3 girls in a row is 1/8. Okay, what about the probability of getting heads or tails when you flip a coin? So let's look at that word or, the union. And I chose this because, of course, it's something that you intuitively know already. The probability of getting heads is 1/2. The probability of getting tails is also 1/2. But that or means you add them together. So the probability of getting heads or tails when you flip a coin is 1. Okay, what about the probability of rolling a 3 or a 4 on a 6-sided die? So you have the probability of rolling a 3 on a 6-sided die. That probability is 1/6. You have the probability of a 4. That's also 1/6. And when I say a 3 or a 4, so either one will be okay, I add those two together and I get 2/6 or 1/3. So let's put this into genetics here. What's the probability of having an albino child if both parents are heterozygous? Yes, we did this already, but now we're going to do it without the Punnett square. So now we're going to look at both parents being heterozygous. And what is the probability of producing an offspring that's homozygous recessive? So this parent has a 1/2 probability of donating the recessive allele. So does this parent. In order to get 2 recessive alleles, what I'm saying is I need this and that. So the probability is going to be 1/2 times 1/2. That's going to be 1/4. And hopefully you remember that that is the exact same result we got with the Punnett square. I feel so good when things work out the way they should. Okay, so squares do get ugly pretty fast, and so the value of probability and understanding probability becomes evident very quickly. This is the dihybrid cross that I did from my Mendelian genetics video. So if you want to see me work this thing, check that video out. You can still, do it with a dihybrid cross on an exam. That's going to take you a while, but anything bigger than that, you're really going to need this probability skill. Look at a trihybrid cross. So we got these parents. Are you really going to do a square like this? I mean, especially on an exam in a timed situation? I don't think so. But understanding probability makes this really pretty easy to do. Okay, so the P's first. What I want is the offspring to have 2 recessive alleles for P. So this parent is heterozygous. So the probability for them to donate little p is 1/2. So is this parent. Same thing, 1/2. 1/2 times 1/2 gives us, for the offspring, 1/4. For the Qs, I want an offspring that is heterozygous for the trait. The only parent with a recessive allele for Q is this one. The chance of the offspring inheriting it is 1/2. The dominant form, the big Q, has to come from this parent, and the probability that it will donate that big Q is 1, because that's all it has. 1/2 times 1 is 1/2. Finally, for the Rs, we want the offspring to be homozygous dominant for R. This parent is heterozygous for R, so the probability of it donating the dominant allele is 1/2. This parent is homozygous dominant, so the probability that it will donate the big R is 1. And once again, 1/2 times 1 is 1/2. So finally, if you want to know what is the probability you're going to get this offspring, you have to multiply these together, because I'm saying this combination and this combination and this combination. And if you do the math, you're going to see the probability is 1/16, which is the answer. And see, that wasn't so bad after all. So we've looked at autosomal recessive inheritance with Punnett squares, and we've looked at autosomal dominant inheritance. The other kind of problem you'll most likely come into contact with is X-linked recessive traits. So these obviously not inherited in Mendelian fashion. They're carried only on the X chromosome. You tend to see interesting pedigrees with X-linked recessive traits. The most common one that we talk about is colorblindness, but we also see things like certain types of hemophilia inherited in this way. We're going to use slightly different nomenclature for this. Because it's carried on the X, we actually use the letter X, and we use X plus to mean normal or wild type, and we're going to do colorblindness. So I'm going to use this superscript C to show that that is the allele for colorblind. Now, because females have 2 X's and males have only 1, the outcome of X-linked recessive conditions will be different depending on your gender. So females can be either homozygous, wild type, normal. Females can also be heterozygous. So this is a silent carrier condition. Females can also be colorblind, but they have to carry 2 copies of the colorblind allele. Males only have 1 X. So males are either normal, wild type, or colorblind. So the difference is that males cannot carry a sex-linked trait in a heterozygous fashion. Only females can do that. So here's a typical problem. What is the probability of having a colorblind child if the mother is a carrier and the father has normal color vision? Okay, for this I highly recommend the Punnett square. It's going to be pretty easy to solve once you do that. So the mother is a carrier, so one of her X's is normal and the other carries the allele for colorblindness. The father is normal. So you just fill out the square and you're going to see what you get. We have 1 female that will be totally normal. 1 female will be a carrier. And for the males, you get 1 that's normal, 1 that's colorblind. So the question, the probability of having a colorblind child is 1 in 4. So there you go, several examples. I hope that they were helpful. As always, I thank you for visiting the Penguin Prof channel. Please support by clicking like and share and subscribe. You can join us on Facebook and follow on Twitter. Good luck.